Let's get back to this issue of the power plant. So let's look at how the discount rate really impacts things. So this is our discounted cash flow analysis. And remember, we started out assuming the discount rate was the same as the firm's or the weighted average cost of capital, or 6.25%. That's what's shown in blue. What happens if we use a lower discount rate of 4%? Well, it doesn't impact anything in year zero, right? So that minus $20 million that we lose in year zero, we're still going to weight that as $20 million because we don't discount anything in year zero. But as soon as we get to year one and onward, you see that using the lower discount rate, or the red bars, are higher, right? And that means that what that effectively means, if you think back to that equation of PV is equal to FV divided by 1 plus R to the T, well, if the R is smaller, that means what you're dividing the future values by in the denominator is smaller. And so the future values in present value terms are higher as you go out into the future. So in other words, if we use a lower discount rate, we value profits from this power plant more highly out into the future than we would if we used a higher discount rate of 6.25%. This shows the sort of the flip of that, right? So again, we're assuming in this case, a higher discount rate than the firm's weighted average cost of capital. It does not affect anything in year zero, that initial capital outlay from shareholders. But as you go out into the future, with a higher discount rate, we are more heavily weighting, or more heavily discounting or subtracting the value of future values or future profits from this firm. So the green bars are all uniformly lower than the blue bars because we're using a higher discount rate. The value in the denominator of that equation, PV is equal to FV divided by 1 plus R to the T, the denominator is larger. And so every time when we put a future value in present value terms, that present value gets smaller and smaller. So what do we do for this particular power plant if we add up all the discounted cash flows? What we get is something that's called net present value. And so this is the sort of the formal mathematical formula for net present value. And it's basically the same thing as adding up all the discounted cash flows. This Greek symbol just means you're adding everything up. At the very bottom of it, you're saying from T is equal to 0 all the way up to some large value of T, which is shown on the top of the symbol. So all that's saying is that we're adding up the discounted cash flows from year 0 all the way up to T, which in this case should be T equals 25. And what we see to the right of that Greek symbol is something in the numerator, C to the T. And so that is profits in year T. And then on the denominator, we have 1 plus R to the T. So R is the discount rate again, and small t is whatever year we are in the project lifetime. So net present value calculations are used to determine whether something is a good financial investment, but also to compare two different investment choices side by side. So what's the impact of the discount rate choice on net present value? Let's take a look. So low discount rates typically make projects or investments look better or more valuable. And that's because if we use a lower discount rate, we are more or equally weighting profits that are made today and out into the future. In other words, we're not discounting future profits as much as we would otherwise. A really high discount rate tends to make projects look less valuable or worse. And that's because whatever project profits come from them out into the future, we're going to weight less strongly. We're going to reduce their value in present value terms. So a general rule of thumb is that the net present value, if you have a positive non-zero value of net present value, those are projects that you might deem as acceptable. But a project with a higher net present value is better than a project with a lower net present value. So let's do this power plant example and calculate its net present value using this equation. And so all we have to do that is go back to our discounted cash flow analysis and simply add up all the present values that we calculated for each future value in years 0 through 25 of the project. Remember, in year 0, the present value was just the initial money that the shareholders paid out in order to help finance the project, so minus $20 million. Year 1 profits of $4.12 million were discounted to equal $3.88 million. Year 2 profits were discounted to equal $3.43 million. Year 3 profits were discounted to equal $3.23 million. And so forth and so on, all the way down to year 25. And if we added everything up, what we would get is a total net present value of $27.79 million for this power plant. So what does that mean? This net present value of $27.7 million might pass the initial test if we use this really simple rule of thumb that the net present value has to be greater than 0. It certainly would meet that threshold. Now let's think about what could cause this coal plant's net present value to change. So if we're just thinking outside of the discount rate itself, we already sort of talked about how the influence of the choice of discount rate on net present value. But if we think about other things, given what you know about the electric power industry and coal plants in general, what are types of different contingencies that could occur out into the future that might alter the net present value of this project? So one would be regulations. For example, what if we decide to build this power plant, and then there's a law that's passed that requires carbon capture and storage, so a different technology, an expensive technology, to be implemented at this power plant, or it taxes carbon emissions. For every unit of carbon dioxide that the power plant emits, it has to pay a penalty. What would this impact in the net present value? So let's go back. A capital cost of $120 million, that's the sticker price of the original plant. If there were an additional requirement that the plant had to install carbon capture and sequestration technology, that would significantly increase the capital cost of the project. That technology is not in widespread use, even though it's technically feasible, largely because it's too expensive. And so having a requirement that a coal plant installs carbon capture and sequestration technology would significantly impact the original capital cost of the project. Fuel costs. What if the cost of coal increases during the lifetime of this power plant? That could also impact the net present value of the project, as well as electricity revenues. Remember, we assumed that it was selling about $42 million worth of electricity every single year for every year, and that was an important part of our calculation of the plant's annual profits. But that might not actually be the case in the future. Demand for electricity might decrease, or competition from other types of generation, whether that's renewable energy like solar and wind, or natural gas power plants might reduce demand for electricity from this specific power plant and decrease its annual revenues. So in those cases, it would affect the annual costs and revenues for this power plant, which would impact its annual profits. So the altered fuel costs would alter how much it pays for coal every year. Competition from other sources of generation or reduced electricity demand would impact how much electricity it's able to sell. So unexpected increases in future costs, for example, increased cost of fuel or environmental regulations that would require the plant to install more expensive carbon capture and sequestration technology, would increase costs and drive the net present value down. Unexpected decreases in revenues would also drive down the net present value. That could be loss of demand to people putting solar on their houses, or loss of demand to natural gas plants because all of a sudden natural gas prices are a lot lower.